Alright, silly people, here's the situation. We have this covariant form of a Lagrangian for a particle of mass m moving through a 4-vector field A alpha, um, and we're going to use the covariant form of the Euler-Lagrange equation to get the equation of motion for this. And so, first thing we need to do, take the derivative of the stuff, the Lagrangian by u mu. So we have minus m over 2, and then this is going to be a bit of a product rule. So let's do u sub alpha del u super alpha del u mu plus u alpha del u sub alpha del u mu. And then this is going to be minus q over c. A alpha, the Vor vector field doesn't really have u component, so we're just going to treat that as constant in u, and then take the derivative of u alpha del u mu. Okay. All of these derivatives are just Kronecker deltas, though, so we have u alpha. This is going to be Kronecker delta with an alpha superscript and a mu superscript. We're going to have a u super alpha, and then a Kronecker delta with a alpha on bottom and a mu up top. Right, and then this is going to be the same sort of thing. It's a alpha times a Kronecker delta with alpha on bottom and mu up top. Right. We're going to act the Kronecker deltas on these now. This is going to change the u to a superscript, so it's u mu. This is going to be also changing u to a superscript mu. And then we got q over c, and this is going to be a mu, raising a to the superscript mu. Pretty excellent stuff. And so we can write this as just minus u mu, adding up the u's, and have that expression there. But then we still need to take the time derivative of that, so d tau del L del u mu. So we get minus m, this is going to be du mu d tau, and then this is going to be q over c dA mu d tau. So the 4-vector potential doesn't actually depend on tau, so we have a bit of a chain rule here. And so we're going to take the derivative of a to the mu with respect to a different subscript so you can capture all the elements. So del x nu, and this is going to be dx nu d tau, which I can also just write, since the time derivative of a position is just the 4 velocity, we have u mu. Because we're actually summing over mu's anyway, we can also just kind of switch around the order of superscripts and subscripts, so I'm actually going to move the mu up here. So this is a mu, and this is going to be u sub nu, right? It's still the same dot product, but yeah. Then we need to take the derivative of the Lagrangian with respect to x mu. And none of these depend on x mu. A alpha does, though. So we're going to have minus q over c u sub alpha, and then this is going to be del a alpha del x mu. And since we're summing over alphas anyway, I'm just going to change the alphas to nus to be notationally consistent. It's going to be del mu alpha nu. Right. So putting together the Euler-Lagrange equation, we have minus m du mu d tau minus q over c del nu a mu u nu plus q over c u nu del mu a nu equals 0. We're going to collect the q over c terms. So we have plus q over c, and then we're going to have u mu on each of them, so u sub nu. And then this is going to be del mu a nu minus del nu a mu. And that's actually the definition of the strength tensor. So we'll collect it like this: u nu f mu nu. And we can write as a final expression for the equation of motion something like this: q over c u nu f mu nu. And that's the covariant equivalent of the Lorentz force equation. So that's just saying that F equals Q times V cross B plus E. So whatever. We got the right equation of motion. And then the next bit of the problem is to actually get the Hamiltonian given all of this junk. And so to find the Hamiltonian, first we need to find the canonical momentum. And earlier in the chapter, Jackson kind of defined the covariant form of the world momentum, p mu, as minus the derivative of the Lagrangian with respect to the 4 velocity. And we have a derivative of the Lagrangian with respect to the 4 velocity. It was just all the way back up here. It was minus m u mu minus q over c a mu. So we'll just have m u mu plus q over c a mu. So that's the world momentum, and then the covariant form of Hamiltonians go like p mu u mu plus L. So all in all, we're going to have just m u mu plus q over c a mu u mu. And then we're going to have the Lagrangian, which was minus m u mu over 2 minus q over c a mu u mu. Right? And it's funny because this term cancels out this term, and we just get a little bit of a m u mu over 2. Right? Let me write that in a way that's not garbage. U mu over 2. Right. Jackson also wants us to talk about the value of this Lagrangian, or the value of the Hamiltonian, I guess. And we don't really know how fast the particle is moving, actually. But we do know what the 4 velocity is going to look like. It's going to be c for the time component and v for the space component in a rest frame. And then also, if you want to do a Lorentz transformation of it, you get vectors of gamma on these. But then the covariant form, you switch the sign. So it's c minus v. Or in the Lorentz transformed version, it's gamma c minus gamma v. Right? But if we're in a rest frame, so we're just going to use this guy and this guy, and if we wanted to set v to 0, or not 0, let's set v to just c. So we'll just have c times whatever unit vector you want and c times whatever unit vector you want, just moving in a direction, I guess. Then we get that the value of h is m, and then if we just do the time components, we get c squared over 2, and then if you do the space components, you get also c squared over 2. So we get a total of mc squared. So Einstein was right!